coming. So we're pleased to have Domagoj. Is it correct?
Yes. Yes.
Almost.
Close enough.
We'll talk about the induced size-Ramsey number. Yeah, please.
Thank you. Thank you all for coming. So I'll be talking about some joint works with Nemanja Draganić, who's at ETH for roughly 2 more weeks. Then he's moving to Oxford, and Sudakov, who's my advisor at ETH. And so we revisit this kind of old problem of finding induced cycles in the size-Ramsey settings with some modern tools and some new ideas, which allows us to obtain much better quantitative bounds. So let's start with defining the preliminary notions. So given a positive integer k and the graph h, we say that another graph g, which I will call the host graph throughout the talk, is k-Ramsey for h if no matter how you color the edges of g into k colors, so each edge receives one color out of k possible colors, you will find a monochromatic copy of h. Okay. And then the famous theorem of Ramsey says that for any number of colors k and for any graph h, there exists a graph which is k-Ramsey for h. Namely, if you take a large enough clique, in any k edge coloring of this clique, you will find a monochromatic copy of h. Okay, and then the k color Ramsey number of h can be defined as follows. This is not the standard way it's defined, but it's equivalent as the minimum number of vertices in the host graph, which is k-Ramsey for h. Now, because we only care about the number of vertices, it's always best to take g to be a clique. Okay, but this formulation perhaps motivates better the following definition, that of size-Ramsey numbers, which was first introduced by Erdős, Fodor, and Shelb. And it's again given a number of colors k and the graph h. It's now the minimum number of edges that the host graph needs to have, such that it's k-Ramsey for h. Okay, so the standard Ramsey number measures the minimality of the host graph in terms of number of vertices. The size-Ramsey number measures the minimality in terms of number of edges. Okay, and clearly these numbers are well defined because, well, we know if you take a large enough clique, it will be Ramsey, so these numbers are finite. And here, the main direction of study is for which graph classes h is the size-Ramsey number linear in the number of vertices. And throughout the talk, lowercase n will denote the number of vertices of the graph h that we want to find in some coloring. Okay, so the first result is due to Beck, who showed that the size-Ramsey number is linear for paths, which answered the $100 question of Erdős. And since then, it's known for several other classes of graphs, namely bounded degree trees, cycles, which I'll mention more later, bounded degree graphs with bounded tree width, as well as logarithmic subdivisions of bounded degree graphs. Now, looking at this list, you might wonder, okay, is the size-Ramsey number linear for every bounded degree graph? This is in fact not the case. In a beautiful paper of Rudl and Semiredi, they show that there are cubic graphs with superlinear size-Ramsey numbers. And their bound was pushed a bit by Tikhomira very recently, but there's still a very interesting conjecture that they conjecture that you should be able to obtain a lower bound which is polynomial. So for, let's say, cubic graphs, there is a cubic graph for which the size-Ramsey number is at least n to the 1 plus epsilon for some positive constant epsilon. This is still not known. I think it's a very nice open problem. Okay, so moving on to the second notion from my title is that of induced Ramsey numbers. Now, again, given a number of colors k and the graph h, we say that a host graph g is k color induced Ramsey for h if in any k edge coloring of g, you can find a monochromatic copy of h, which is an induced subgraph in g. And then the k color induced Ramsey number of h is again the minimum number of vertices that the graph needs to have so that it can be k color induced Ramsey for h. Okay. So just to be on the same page, suppose h is a 5 cycle, and in your graph you find something like this. So it's a red 5 cycle, but there's a blue edge across. So this would not be good. So this 5 cycle should be induced in the entire graph G, not just in the respective color class. Okay. And it doesn't follow from Ramsey's theorem that these numbers are actually defined, but it was proven by several groups of authors that these numbers actually do exist. And here the main question is, okay, can you give a good bound for the induced Ramsey numbers of graphs on n vertices? Here the best upper bound for 2 colors is exponential in n log n due to Kohayakawa and Sudakov, whereas Ehrlich conjectured that it should be exponential in n. And the lower bound is of course exponential, coming from the standard Ramsey numbers, because for cliques it's exponential. Okay, I will not talk more about the induced Ramsey numbers. And now, combining these two notions, we arrive at the main definition of this talk, of induced size-Ramsey numbers. And you can probably guess the definition. So given a number of colors k and the graph h, the k-color induced size-Ramsey number is the minimum number of edges in a graph, which is k-color induced Ramsey for h. Okay, so just to be clear, I give you a number of colors k, I give you a graph h, find me a graph G with as few edges as possible, such that no matter how you k-color the edges, you can find the monochromatic copy of h, which is an induced subgraph in the host graph, so there could be no other edges on this set of vertices.
Can I ask something?
Yes.
So in the previous page, I wonder that, for instance, if H is not a if H is not a complete graph and G is a complete graph, and
No, so the point is that G, you can choose G whatever you want. So if H is not a complete graph, you should not choose G to be a complete graph.
right. So what do you mean by these numbers exist? Sometimes it doesn't exist, or
So it's not a priori clear that for any k and any h there is a graph G which is k-color induced Ramsey for h.
Oh, you mean
So I give you a graph H, let's say a 4 cycle. You need to find me a graph G.
Oh, I see.
Such that no matter how I, let's say, 2-color the edges, you find me a 4 cycle in one of the colors with no other edges.
I see. So there exists some graph with.
There exists some host graph, yes, exactly.
Okay.
And here the n denotes the number of vertices of h.
Yes, and throughout the talk, lowercase n is always the number of vertices of h. Yes. Okay, are these definitions now clear? If not, please ask, because the rest of the talk won't make any sense. Okay, good. So, as I mentioned, for cycles, Haxell, Kohayakawa, and Łuczak in fact proved that the induced size-Ramsey number of cycles is linear in their number of vertices. So to be more precise, for every k, which is number of colors, there is some constant c, which depends on the number of colors k, such that the induced size-Ramsey number of a cycle of length n is at most c times n. And of course, this translates to the same bound for the path on n vertices. Okay, and throughout the talk, so I will be talking about this problem. What is the best value of this c that we can put in the theorem above? Okay, so the regime I'm interested in is k is the number of colors, and n is much larger than k. Okay. And we want to know how should this constant c grow as the number of colors grows. So here is what is known for the size-Ramsey and induced size-Ramsey number of paths and cycles. Again, I'm interested in the value of this dependence on the number of colors. Okay, so let's first talk about lower bounds. Dudek and Bradač show that for the normal size-Ramsey number of paths, the k colors, you need at least omega k squared times n edges. And of course, this translates to a lower bound for all of these other problems, because if you cannot find the path, you cannot find an induced path, you cannot find a cycle, you cannot find an induced cycle. And Javadi and Miralei observed that for odd cycles, you can get an exponential bound of roughly 2 to the k, exponential lower bound. And this is for the size-Ramsey problem, and of course then for the induced size-Ramsey problem for odd cycles as well. Now, regarding upper bounds, Krivelovich showed that the size-Ramsey number of paths is at most k squared log k times the length of the path, so there's a log k gap here which would be interesting to close. Then for the induced version, for the induced size-Ramsey number of paths, Draganić, Grok, and Krivelovich obtained a bound roughly k cubed times n. Now for the size-Ramsey number of even paths, Javadi and Miralei obtained a polynomial bound in the number of colors, something like k to the 120, and for odd cycles, they obtain exponential in k squared bound. Okay, and for the induced problem, the best bounds we have, actually the only bounds we had before our work, are from this paper of Haxell, Kohayakawa, and Łuczak, and they're not explicit. They're of some tower type dependence on the number of colors because they use sparse regularity lemma. So in our paper, we improve some of these bounds. So again, we think of k as being a small number of colors and n being much larger compared to k. So for the size-Ramsey number of cycles, we obtain a bound which is exponential in k times the length of the cycle. And for the even induced cycles, we obtain a bound which is polynomial in k, actually k to the 102 times the length of the cycle. And for odd cycles, we obtain a bound which is for the induced size-Ramsey problem, which is exponential in k log k times the length of the cycle. Okay, so coming back to this table, the bold values are our improvements. So for induced size-Ramsey number of even cycles, we have k to the 102 times n. Of course, this translates to the same bound for the non-induced problem. So we improve this k to the 120 to k to the 102. Okay, it's not a big improvement. And in fact, we could probably push this to something like k to the less than 10, but not close to k squared. For the size-Ramsey number of odd cycles, we obtain an exponential bound in k, which is optimal, of course, up to the base of the exponent, which is far from optimal for sure. And for the induced problem, for the induced size-Ramsey number of odd cycles, we have a bound which is exponentially k log k, so there's this extra log k in the exponent, which we think should not be there, and I'll say a bit more later. Okay, are there any questions about the results, about the statements?
So my upper bound is like constructions, right? So
you need to construct a graph, and you need to show that no matter how it's colored, you can find monochromatic cycle or induced cycle, depending on what the problem is. Okay, so the rest of the talk will be focused on giving you some of the ideas of our proofs. And first, it makes sense to say what was done previously. So, kind of in these problems, a natural host graph to take is the binomial random graph with some constant average degree, where this constant depends on the number of colors. Okay? And the number of vertices is, again, some constant which depends on the number of colors times the length of the cycle that you want to find. Okay? And then you take this random graph, you get a coloring of its edges, then you have some way of choosing a suitable color. Now, in different approaches, this suitable means different things. For Haxell, Kohayakawa, and Łuczak, they want to find a triangle in the sparse partition. A weaker suitable condition would be you take the majority color. There are various approaches. And then you either, depending on what suitable means for you, you either guarantee that you find your induced cycle, or if you took a weaker suitability condition, you maybe say, oh, I either find the cycle that I want, or I find a large subgraph which doesn't contain this color, and then I can recurse inside this large subgraph. And our main observation or our main idea is that with this approach, at least it seems that it should be easier to find a cycle of some approximate length than of length exactly n. Okay, so if I want to find a cycle in this interval between 0.9n and 1.1n, well, at least it seems it should be much easier than to find a cycle of length exactly n. Okay, and then we design a host graph to exploit this idea. Okay, so let me give you the construction, and I will focus on the kind of the hardest case. We want to find an induced cycle of some odd length n, and we want to show that the induced size-Ramsey number of this cycle is at most exponential in k log k times n. And then in the end, I will tell you how to modify the proof to get the different results. So first, we find some small gadget graph f, which only depends on the number of colors, which is k induced Ramsey for the 5 cycle. Okay? So it's some small graph. No matter how you k color the edges, you find a 5 cycle in one color, which is an induced subgraph. Okay? Then you place a big linear number of copies of this gadget graph on something like a constant times n vertices. Again, this constant c1 and c2 depend on k, but I will not write now the dependence on k. Okay, and now you build an auxiliary graph G. So my host graph I will denote by gamma, and the auxiliary graph I will denote by G. So you build the auxiliary graph on the same set of vertices, where what you do is you look at every copy of f that you placed. Now you know after the coloring there is some monochromatic 5 cycle there as an induced subgraph. You take one such 5 cycle, you take 2 vertices which are not adjacent on the 5 cycle, and there you put an edge in the auxiliary graph, and you color this edge by the color of the 5 cycle. Okay, this is a lot of details, so here are some pictures. So first, you decide each of these circles represents the vertex set of one of the copies of f. Okay, so you can think of it as a uniform hypergraph. Okay, now inside each of these circles, I place one copy of f, where f is my gadget graph. Okay, this is my host graph, gamma. Now, the adversary comes and gives you a coloring of this graph. Now, in each gadget graph, by definition, we know we can find one 5 cycle, a monochromatic 5 cycle, which is an induced subgraph in this graph. Okay, maybe you find many, but you just take one and take exactly one pair of vertices which are not adjacent. Okay, and then on this pair you put an edge in the same color to obtain your auxiliary graph G. Okay, so for example, this top left gadget graph, we find a red 5 cycle. We took these 2 vertices and connected them by an edge in the auxiliary graph. Now you get a graph that looks something like this. I mean, in fact, it will be a bit denser. It will have big constant average degree, but that will be kind of horrible to draw. So now we have this graph, and most of what we do is focused now on this auxiliary graph. Okay, so why did we do all this? Well, remember what I told you. The main idea is it should be easier to find cycle of approximate length in some random-like graph than of exact length. Okay, so what I claim is that if we find a monochromatic cycle in this auxiliary graph of length between n over 3 and n over 2, and it has some additional good properties, which I will not define formally, this should give me an induced monochromatic cycle of length n in the original graph, which is exactly what I want. Okay, so suppose in the auxiliary graph you find this blue 8 cycle. Okay, what does it mean? Well, remember that each of these auxiliary edges comes from some blue 5 cycle, and we connected two vertices which are at distance 2 on the 5 cycle. Okay, so let's forget about the auxiliary edges. I have a picture that looks like this. Now for each pair, I can either choose a path of length 2 or a path of length 3. Okay, so from this 8 cycle, I can get any cycle length between 16 and 24. Just by choosing a path of length 2 or a path of length 3 between each of these pairs.
So no overlap between these 5 cycles?
Yes. So that's exactly one of the conditions of it. So you get a cycle like this, and okay, how do we know this is an induced cycle in the original graph? So one of the conditions we require that these ovals, so remember each of these ovals represents a vertex set of one of the copies of f. So one thing that we require is these ovals intersect only like in the picture. So they only intersect in these vertices which are drawn. Okay, that's one thing we need. And another thing, okay, suppose now there's an edge connecting two vertices like this. Now if you have this edge, the cycle is not induced, which is not good. Well, this edge must come from some copy of f that we placed. Right, so there's some oval which intersects this picture in at least 2 points. And I just want to say, okay, I want to find such a picture where no such oval exists. If I can find it, then I know that my cycle will be induced. So with this approach, our task essentially reduces to the following. We want to find an induced cycle of some approximate length, so between, let's say, n over 3 and n over 2, in a graph with local sparsity. What does it mean? Well, remember that our auxiliary graph was obtained by putting edges where each edge is from one of these copies of f. And the copies of f are placed randomly, so in the auxiliary graph you cannot have too many edges on a small set of vertices. And now I have this graph, I have some subgraph of this graph because I take the majority color. And I want to claim that in this graph I can find a cycle which looks like this. And I want to say that this is essentially the same as finding an induced cycle in a graph with local sparsity. Of course, we have a much more complicated condition. We have these ovals that we need to care about, which gives a kind of more complicated inducedness condition, but which introduces a lot of technical details, and you need some tricks to take care of it. But the meat of the argument is in this kind of simpler problem. And now, the main tool that we use is a modification of the DFS algorithm for induced paths, which was developed by Draganić, and Krivelović. And this is how they get their bound for the induced size-Ramsey number of paths. Now, as I mentioned, to get different results, we use different gadget graphs. The rest of the proof is the same, and you need to tweak the parameters a bit. So, as I said, the case where you want to find an induced odd cycle is the hardest, and here we want F to be a gadget graph, which is k-color induced Ramsey for the 5 cycle. And I'm claiming that if you take Alan's construction of a dense pseudo-random triangle-free graph on roughly exponential in k log k vertices, this graph has this property. In any k edge coloring, you can find a monochromatic 5 cycle as an induced subgraph. Now, if you want to find an even induced cycle, we take the gadget graph, which is k-color induced Ramsey for the 6 cycle. And here you can just take a dense C4 free bipartite graph on k to the 6 vertices. Okay, so this explains why here we get the polynomial bound, and here we get bound which is exponential in k log k. And so for the even induced case, now you find an induced 6 cycle. So then to build the auxiliary graph, you connect 2 vertices which are at distance 2 on the 6 cycle. Okay, then if you find the cycle in the auxiliary graph, between every pair of consecutive vertices, you can choose a path of length 2 or a path of length 4. So you can get all even lengths in some interval. Okay, and finally, for the size-Ramsey number of odd cycles, now not necessarily induced, we want the gadget graph F to have the property such that any k edge coloring contains a monochromatic odd cycle. And here you can take F to be the clique on 2 to the k plus 1 vertices. Okay, and similarly, once we have such a cycle, in the auxiliary graph we connect 2 vertices which are almost on the diameter. And put an edge there in the auxiliary graph. So, are there any questions at this point? Okay, so in the remaining part of the talk, I wanted to give you a bit more details of the proof, but I realized that there's a lot of details and it would probably not be possible to explain it without just confusing you too much. So instead, I will present you this argument of Draganić, Glock, Krivelovich for finding induced paths, because this is kind of the main tool that we use. So we find our cycles, we find our induced cycles in kind of 3 stages, and 2 of these stages use their arguments as basic building blocks. So I think it's a very nice argument. I think it could be useful maybe for other applications.
And
yes.
What about the even case for non-induced?
For non-induced?
Yeah, for the even.
It's the same bound, so it's
So
it's a strictly.
To the induced case, right?
So yes, I mean if you find an induced long cycle, it's also a normal cycle. So yeah, we did not actually write the better bound for the non-induced case. So we just claim the same k to the 102 bound. Okay, so in the rest of the talk, I will present you the proof of the following theorem. So the k-color induced size-Ramsey number of a path of length n, so the order k cubed log to the 4th k times n. Okay, I'm lying a bit. I will not present you this exact bound because I don't want to be very particular about the numbers, but I will just present you the argument, and you can work out the optimal numbers which would give this bound. So I will show that you can just put some polynomial here in K. In fact, this polynomial will be K to the 9. Okay? So you take G to be binomial random graph on big N vertices with H probability k squared over n. Okay. So let me just write you two very easy properties of this random graph which hold with high probability. First, well, we know the number of edges. N times k squared over 2. And second, for any set of vertices, W, which is not too big, let's say 2 n over k to the 7, there cannot be too many edges. Okay, so what this is saying, any subset of vertices, any linear but small enough linear set of vertices cannot induce a subgraph of average degree 3 or more. Okay? And this 3/2 you can push to 1 plus epsilon. But not below because, well, in a random graph you expect to find a cycle of logarithmic length, which is a subgraph of average degree 2. Okay, and we're saying if you forbid average degree 3, this holds for linear size sets. Okay, so I will not. So this is a simple first moment calculation. Okay, so this will be my host graph. Now, what you do is let's say that let red be the color which appears most often. I call G red the set of like the red subgraph, and I will clean it for mean degree. So I remove vertices of very small degree to obtain a graph G prime which has minimum degree at least, let's say, k over 4. Okay, so just to convince you of the numbers, G has average degree k squared, so one of the color classes has average degree k, so I can remove vertices of low degree to get a subgraph with minimum degree at least k over 4 in red. Okay, now what I want to show is there exists a path in this red subgraph of length n over k to the 7.5 which is an induced subgraph in the original graph. Okay, so a monochromatic path in G prime. Path in G prime of this length, which is an induced subgraph in G. Okay, so if you take n is this number, then you get this path. And the idea here is to use a DFS algorithm. So what does the algorithm do? We maintain a partition of the vertex set of G prime into the following four sets: P, U, T1, and T2. Okay, so what are these sets? So P throughout the algorithm will be path in G prime, which is induced in G. Okay, so this is the object that we want to find. U will represent a set of unused vertices. What does it mean unused? They were never okay, so these sets evolve. U at each point is a set of vertices which have never appeared in the set P. Okay? And T1 and T2 I will call trash sets. And I'll have two different types of trash, trash 1 and trash 2. Okay? And both of these sets contain vertices which at some point in the algorithm were in P. Now, let me present you the algorithm. So you start with U is the whole set. The other two sets are empty. So every vertex is unused. You take an arbitrary vertex from U, and you start building a path from this vertex. Okay? So I take a vertex. Let me draw it in red. I find the red edge in G prime for another vertex. Now, when I do this, I take a neighbor in U, I add it to the path P, and then remove it from the set of unused vertices. Okay. And you continue. Okay, so now three things can happen. So let me denote by X the last vertex on this path. So case 1, X has no neighbors in U. So what do we do? Well, we cannot continue, so we need to do something. We move X from the path. So this is the path. This is the set P, which is a path. We move X from the end of the path to the first trash, T1. Okay, so we remove X, and then again from this vertex we try to continue the path. Case 2, Okay, so when I said the path is induced, I lied a bit. It's induced except for maybe the last vertex. Okay, so perhaps the last vertex has an edge back to the path. This edge does not have to be red, but any edge is not good for us. Okay? So if X has another edge to P, another because it obviously has this one edge, but it has a different edge back to P, then we move it from P, but now to the other trash set T2.
Oh, so is X a vertex of P or?
Yes, X is the last vertex of P. So P is an induced path except maybe for the last vertex.
Oh, just accept the last. Okay.
Yes. Okay, and I'm running out of boards. Okay, let me put this down. And in the third case, we actually proceed. So the first two cases did not happen, which means that now the path is induced, even with the last vertex, and the last vertex has some neighbor y, u. Okay, red name. Okay. Okay, so we extend the path by attaching y. And this is it. Okay. Now we want to show that this algorithm should at some point have a path which is long, of length at least n over k to the 7.5. Okay. So what we do is we freeze the algorithm at some point because we want to obtain a contradiction. So we stop when one of the following two things happens. A, the first trash grew large, or B, the second trash grew large. Okay? And here, you need to be careful about the numbers. So A, when the first trash has this size, or B, the second trash has this size. Okay, so we stop when either the first trash grows to n over k to the 7.5, or the second trash grows to size n over k to the 7. Okay. Now, so suppose that the path is always short, otherwise we are done. And now we consider two cases, depending on which of these two happens first. Okay, so suppose that A happened first, the first trash grew large. And let's consider the set W, which is P union S1, sorry, P1 union T2 at this point. Okay, so I want to show that W is a small set which has too many edges and thus would contradict property 2. Okay, so first let's argue about the size of W. Well, size of P is at most this. Size of T1, well, we stopped when it's of this size. And we assume that A happened first, so T2 is at most this size. Okay, if you gather all these up, these two are small. This is the biggest term, so it's at most at 1.1 times n over k to the 7. Okay. Now I want to say that W spans many edges in G prime, and thus many edges in G. Okay, so what's the main thing? We know that we put many edges in this trash set T1. When do we put many vertices in this trash set T1? When does a vertex end up here? When it has no neighbors in U. Okay? And notice that, so all of its neighbors are in P or in S1 or in T1 or in T2. Sorry. And if a vertex is on the path or in the trash, it always stays either on the path or goes to the trash. Okay? So every vertex that we put in T1, at the point where we put it, it had all of its neighbors either in P or in T1 in T2. And throughout the algorithm, those vertices will stay either in P or in T1 or in T2. So in total, we get that W spans at least T1 times the minimum degree, let's say over 2 because we might double count many edges. And we know that this is at least n over k to the 7.5 times k over 8. So it's n over k to the 6.5, which is definitely much bigger than 3/2 times the size of W. Okay, and now in the second case, B happened first. And we consider the same set and the same inequality applies. So again, we have a set of size most 1.1 and over k to the 7. Now, again, we want to claim that this set is too dense. So where do we get the edges from? So we know that this second trash set is large. And when does a vertex end up in the second trash set? If it has another edge back to the path. And again, this edge, so now it has two neighbors on the path. One that we use to reach X, and another one that kind of ruins the inducedness of the path. And again, all the vertices on the path will either stay on the path or get moved to some trash set. But anyway, they will always be inside this W. So for every vertex in the trash set, we obtain two edges. And now there's no double counting. Now there are genuinely two new edges. Okay? And now these edges are in G, not necessarily in G prime. But that's okay. We get at least two T2 edges. And if you look at the numbers, T2 has size n over k to the 7, which is much bigger than, right, it's bigger than 3/2 times W now. The number of edges. Oops. Okay, are there any questions about this proof? I wanted the slides. Not responding. Okay, so let me finish the talk with kind of the main remaining open problem. So we think that for odd cycles, the induced size-Ramsey number should be exponential in the number of colors times the length of the cycle. And with our approach, it would be enough to construct a gadget graph which has the following property. So it's a graph on exponential in k vertices, hence has exponential in k edges, such that no matter how you k edge color it, you find a monochromatic cycle, the monochromatic odd cycle of length of these 5 as an induced subgraph. Okay, so if you find such a gadget graph with our machinery, you get the bound above for the odd induced cycles. That's all I have to say, so thank you.
Thank you. Any questions?
Yes.
Once you find a long monochromatic path, how do you close it up to the next?
So there's yes, as I said, there's 3 stages. So roughly speaking, so we find the path. They want to find some trees which expand exponentially here. And if they expand exponentially, eventually, these vertex sets will intersect, and this should close the cycle. But the inducedness condition becomes kind of complicated here. You cannot hope to find everything here induced, so we just require that every root leaf path like this is induced. And then this expansion you also cannot do, at least we didn't know how to do it with one argument, we will do it in 2 steps. First we expand to some linear size set. Actually first we find an expander in our red subgraph. Then we clean it for minimum degree. Then we do this whole business of finding induced path, finding these expanding trees. And once you expand to linear size sets, so these 2 arguments are with this type of argument. Once you expand to linear size sets, you remember that you live inside an expander, and then you can keep expanding. But this kind of local sparsity breaks down once you get to very huge sets, so you cannot continue doing this type of argument. And there's a bunch of details are swept under the rug there, but that's the rough idea.
I think.
Yes.
So it seems from the proof that you construct a graph where you simultaneously, so no matter how you color by k colors, you have induced cycles of lengths in certain interval at the same time.
Yes, so from big constant times log n to linear. So let's say if n is the size of the host graph, we find cycles of any possible length between some big constant log n to epsilon n, where this constant and epsilon depend on the number of colors.
And they all of the same color, or are they all distinct color?
Yes. In one color, we can find the color such that it contains all of these cycles.
I see.
Yes.
Is it still interesting if you relax the problem to just being induced within that color?
Yes, so this is called weak induced Ramsey numbers. It's, I think, less studied than the induced Ramsey numbers, but yes, you can ask this question as well.
compare, like, do people think about the like a game version where you have a maker breaker and try to
Make a breaker for induce.
like, do we expect to have a lower? I mean, probably it's lower number. Right? You might have, you don't need a huge graph to construct that.
I honestly don't know. I'm sure there are some results, but I don't know.
It looks like at some point in your proof you're going to get a cycle in a hypergraph, like a loose cycle, an induced loose cycle in a hypergraph. Is that?
So not exactly. So we pass to this auxiliary graph.
Yeah.
So it's a graph,
Yes.
and we want to find the cycle in this graph.
Yes.
But the induced condition is much more complicated. The induced condition is something defined on this hypergraph.
What I thought, so you
But the
have
cycle itself is in the graph.
The cycle is in the graph, but I thought the inducedness condition for the hypergraph corresponding to the edges of the graph
Yes. So
would be a cycle in the hypergraph, would be an induced cycle in the hypergraph, but I'm not sure.
but it's kind of
Well, maybe it's
an
not
induced
exactly,
cycle in the
okay.
hypergraph does not give you necessarily a graph.
Yeah, okay, I think it doesn't go, yeah. What I was wondering is if you had considered, like, have people considered the hypergraph version of these questions? Like,
Not that I know of.
okay.
But for example, I mean, our result would give you something for the hypergraph version, because kind of what we do is say in each. So what is a loose cycle? You find two like hypergraphs. If they intersect, you can kind of go from one to the other. But we are saying, in fact, you can adversarially place edges inside, so that I think it's
Yeah,
strong.
you need to find something stronger than the
Yes.
induced cycle in the
Yes.
hypergraph. But it looks like your coloring for the graph, you can obtain the coloring of the hyperedges based on how the hyperedges are defined, as the color would be based on the induced cycle you find inside it. And then within that coloring of the hyperedges, because you find a cycle, I don't know. I'm
Yeah,
not sure.
so
You might,
off the top of my head, I'm not sure.
Yeah,
if it's
yeah. I was
exactly.
just curious if it was.
But I would feel that our methods would imply something
Okay,
in the
yeah.
hypergraph setting.
Are there any explicit construction for small values of cycle where you can maybe coming from algebra or which has this property?
But which would be tight in this setting, I don't know. Because it seems that, I mean, at least for lower bounds, it's kind of difficult to use the condition that it should be induced. So these lower bounds, as you saw, they just work for the normal version, not induced. I mean, they of course translate to the induced version.
Yeah.
So I doubt that you could get something tight. I mean, perhaps you could, but I think it would be very hard. And also, I think none of these, even for small cycles, is known, even for the normal size-Ramsey version, not just induced.
So, but the construction, the proof is, in a sense, it's random constructions, right? So,
Yes.
so we don't have deterministic constructions.
You could probably de-randomize this, because we're not using a lot of properties of the randomness. We're just using that it's locally sparse. I would assume you could de-randomize this, but it's not my expertise. I don't claim
Okay.
that it can be.
Right. Any other questions? So let's thank the speaker.